Well, welcome back to the second lecture in our series. Today we're going to explore annuities. You'll find them in all over the place in finance. So before we do that, though, let's go back and very quickly review some of the things we've learned last time. We looked at our building block equation. We saw how it was developed, and we learned how to solve for the interest rate and for the number of periods. The very key thing to using this equation is to be absolutely certain that the interest rate you use corresponds to the size of the period. N is the number of periods, and the interest rate and the period must correspond. Today we're going to examine annuities. An annuity is a stream of equal payments. They are equally spaced throughout time. And this timeline shows us an end payment annuity. The first payment comes at the end of the first period, and the annuity ends with the nth payment. These payments are equal, and we define them as PMT. N is always the number of payments in our annuity equations. And quite often, we want to find some equivalent lump sum amount that consolidates all of these payments at a point in time. Frequently, that point in time is right here, one period before the first payment, or right here, one instant after the last payment is made. If our annuity, for example, is a loan, like a mortgage or a car loan, we'll want to, the amount we're borrowing would be a lump sum amount right here, one period before the first payment is made. We also may want to look at a future value equation that consolidates all of the payments an instant after the last payment is made. This would tell us the future value of a series of deposits into a savings account, for example. Suppose we want to find some equivalent lump sum located precisely one full period before the first annuity payment. We would use our building block equation to bring each of these future payments back in time and consolidate them right here at time zero, where this lump sum money bag is. So we bring payment number one back one period, payment number two back two periods, and so on. The equation is simply the building block equation, time after time after time. We bring the first payment back one period, the second payment back two periods, the third payment back three periods. The last payment would be brought back n periods in time. Now, if n is very large, that equation can be lengthy. A 30-year monthly payment mortgage, for example, would have 360 payments. Fortunately, there's a way that we can manipulate this geometric series until we make it a closed form equation of this form. The present value is equal to the annuity payment times this factor, 1 plus the interest rate to the nth power minus 1, all divided by 1 plus the interest rate to the nth power times the interest rate. The important thing to know is that both these equations, this long open form equation and the closed form counterpart, do exactly the same thing. They get exactly the same answer, and they both deal with this timeline where they consolidate the payments one full period before the first payment is made or received. Now, I could show you the algebraic manipulations that are involved to do this, but I don't think we really have time for that. So I would refer you to a section of your primer, one of the appendices, that talks about geometric series and closed form equations. That will walk you through the whole process of turning this open form into the closed form that we can use. And when n is very large, this is the equation we want to use. And this is the equation that is programmed into your financial calculators. Do you have any questions so far? Now let's look at the equation for the future value of an annuity. Here, we want to find an equivalent lump sum amount represented by that money bag located just one instant in time after the last payment has been made or received. We might be making monthly deposits into a savings account, and the question might be, how much money do we have in our account after the 100th deposit? Again, we're going to use our building block equation, and we use it over and over to construct a geometric series. What we're doing is taking this very first payment and we're moving it to time n. Well, since the first payment is at the end of the first period, we will be moving it forward in time n minus 1 periods. So we'll move it from here to here. The second payment will move forward in time n minus 2 periods. The third payment n minus 3 periods, and so on. This second to last payment, we only have to move forward 1 period in time. And the last payment is sitting exactly where we want it to be, so it doesn't earn any interest. Excuse me. Again, this is an open form equation. It's difficult to use if n is large, but again, because it's a geometric series, we can manipulate it algebraically until finally it becomes a much simpler closed form equation. The future value of our stream of payments is equal to the payment amount times this factor, 1 plus n to the nth power minus 1, all divided by the interest rate. And again, this is the factor that is programmed into your financial calculators. But even if you're just using your y to the x button, you can very easily work with this equation. As before, both of these equations do exactly the same thing. They move all the payments to the point in time the last payment is made. They will both give you exactly the same answer, but the second equation is much easier for us to use. So a quick recap. We have a present value equation. It's also equal to the open form, and this open form equation moves every payment back to time 0, one period before the first payment is made, consolidates them all there. The future value equation consolidates all the payments in an instant after the last payment is made. The open form, the closed form, both will give you exactly the same answer. Now, it's interesting that both the lump sum at time 0, if we use the present value equation, or the lump sum at time n, if we use the future value equation, both of these lump sums are equivalent to our series of payments. Given some number of payments, given some interest rate, and depending on how far apart the payments are spaced. This PV money bag is equivalent to the payments. The FV money bag is equivalent to the payments. So obviously, this present value amount is equivalent to the future value amount if we moved it to the same point in time. Well, let's try that. Present value is the payment times this factor, 1 plus I to the nth power minus 1, divided by 1 plus I to the nth power times the interest rate. And if I take this amount right here, call it it's some lump sum amount, and if I want to move it from here to here, I'll simply go to my building block equation, present value times 1 plus I to the nth, and it should be equal to my future value, the equation for which is payment times 1 plus I to the nth minus 1 over I. And obviously, a little canceling out and we can see that this equation and this equation are equal now, once we've moved this present value amount to the time in the future. You can see how easily they're both connected. They're connected by our building block equation. So any questions so far? These annuity equations and annuities are a little more complicated, even though they are just a stream of building block equations. They're a little more complicated, and certain time value rules apply to them. The first rule is very similar to the rule we learned about the building block equation, and that is that I, the interest rate, must correspond to the time between payments. For example, if our payments are 3 months apart, quarterly, I must be a simple interest rate spanning a 3-month period. N was the number of periods in our building block equation. It still is, but more importantly, it is the number of payments. Always. Don't break that rule. And the other thing we have to remember, and this is easy, I think, to make a mistake here. You have to remember what these equations do. The present value equation consolidates all payments into a lump sum, one period, before the first payment is made. The future value equation consolidates the payments into an equivalent lump sum at the point in time the last payment is made. And here's one final time value rule. You can only compare two sums of money when they're both at the same point in time. You can only add two amounts of money together only when they're at the same point in time. You can subtract one amount of money from another only when the two amounts are at the same point in time. Often, we'll have to consolidate our annuity into either a present value or a future value, and then move that lump sum to a desired point in time. We'll see that in some of the problems we work later. Any questions about the rules? Because now you have all of them. They're not that extensive, but you can't afford to break any of them and get the right answer to a problem. Questions? Oh, one last thing. Here is a very kind of a special kind of annuity. It's called a perpetuity. A perpetuity is just an annuity that never ends. The payments go on forever. N, the number of payments, approaches infinity. So obviously there's no future value equation for this, because the future value, we would never get there, and if we did, it would be an infinite amount of money. But because interest reduces the present value of each payment, and finally to a point where additional payments only add an infinitesimal amount to the present value, we can find a present value lump sum for an infinite stream of payments. The equation is similar to what we had with an annuity. We just don't have an end. We bring the first payment back one period, the second payment back 2 periods, and so on. We consolidate all of the payments one period before the first payment's made. This equation can also be manipulated until we get a fairly simple answer. Present value of a perpetuity is equal to the payment amount divided by the interest rate. So we could get into a complicated derivation of this formula too, but we don't need to. In fact, there's a very intuitive way to understand this formula. Let's just imagine that you have found a bank that is guaranteed to stay open forever and will guarantee you 7% annual interest compounded annually on any deposit you might make. And you've just made a $1,000 deposit. How much money can you take out of that bank account at the end of every year forever? We have a guaranteed 7% annual interest rate compounded annually. We've just deposited $1,000. How much can we take out of our bank account every year and do that forever and ever? Well, the answer's $70. Because every year, our $1,000 investment will earn $70. And we can take it out and never dip into our $1,000 principal at all. If we take out more than $70, we'll begin to erode the original $1,000 deposit, and then eventually it will be gone. But we can take $1,000 forever. And of course, 1,000 is equal to the $70 payment divided by 0.07, the interest rate. At this point, you might be thinking, nothing goes on forever. Why do we need an equation like this? And that's true. I guess nothing is going to go on in perpetuity. However, often we encounter situations where an annuity, we know it's going to continue for a long time, if not forever, and we don't know how long. The annuity equation might be appropriate. And also, when n gets fairly large, 50 or so, you won't have a large difference between the present value of, say, a 50 or 60 or 70 payment annuity and the present value of a perpetuity. So this perpetuity equation is often gives you a very good, quick, estimated answer. Okay. Well, that's all the mathematics behind annuities. Now all we need to do is get a little practice using them. Now, what I'd like to do, you have a handout called Day 2 Problems, and you have another handout that works the problems. And I'm going to work them right now, but I'm going to work them quickly. My advice to you is maybe put those two handouts aside and just watch as we work these. I know that that's going to be hard for some of you to do because I know you're compulsive note takers, but you have the blank sheet to work on your own later, and you have the answers. So I think we might make best use of our time just by watching some of these work, because I don't think you can do these as fast as I'm going to do them, and I took the liberty of drawing the timelines even before we started. And I think I'll take the liberty of getting the answers too. So, our first problem, we're going to receive 14 end-of-year payments of $1,000. What is the value today if interest is 0.062 compounded annually? Well, here's the timeline. The first payment is one period away. There's 1 year between payments, and the interest rate is a simple rate across 1 year. It fits the payment. It fits the time between payments. So we can very quickly solve this using our present value of an annuity equation. The present value at time 0 is equal to the payment amount times 1 plus the annual interest rate. I take it to the 14th power because there's 14 payments. The answer is $9,180.95. I will give you some time right now to see if you can't recreate this with your calculators. But then we're going to speed through very quickly. My advice is to start at the top. Take 1.062 to the 14th, subtract 1 and store it. Add 1 back, and you have 1.062 to the 14th again. Multiply by 0.062. Now, that 1 over x button is nice to have, because if you hit the 1 over x button, you can now multiply times the numerator which you have in storage. Okay, let's go on. A little practice with that. You'll be surprised how fast you can get. This next problem is essentially the same problem, but with one slight change. This time we receive 14 annual payments of $1,000, but the first payment is received today. Again, the interest rate is 0.062, compounded annually. It fits the time between payments. And if we throw the present value equation at this, we'll get that $9,180 answer again, but it won't be the correct answer to this problem. Why? Where is my lump sum of $9,180 sitting in time? 1 year ago. We have consolidated these payments right here, time minus 1. And so we're at minus 1 year. So if we take the 9,180 and use our building block equation, we can move it 1 year forward in time to time 0 where we want it to be, and it grows to $9,750.16. Again, you have all of these answers, so. Number 3 is a future value problem. With this one, we're going to deposit $1,000 at the end of each year for 10 years. The final deposit is made at the end of year 10. The savings account pays 7.4 annual interest, compounded annually. How much will we have in 10 years? Here's the timeline. We're trying to consolidate right on top of the last payment. And the future value equation will do this for us. N is 10, the number of payments, always. And the answer is $14,080.26. And the future value you can do with your calculators very quickly without even storing anything. Just start, take 1.074, y to the x button, 10, minus 1, divide by 0.074, multiply by 1,000. With the future value equation, you don't absolutely need to know when the payment started, but you need to know when that last payment occurs, because that's where you're going to consolidate the payments. And of course, you need to know the number of payments. And so really, number 4 is essentially the same question. The payments began earlier. You deposit $1,000 a day, $1,000 at the end of each year for 9 years. 10 deposits. The final deposit's made at the end of year 9. How much money do you have in the account at the end of 9 years? The interest rate stayed the same, and so the answer is the same. Now, if the question had asked, what do you have at the end of 9 years, or 10 years rather, we'd have had to multiply this by 1.074 to the first and moved it forward a year. But the future value equation always puts you right on top of the last payment. And number 5 says, you're going to deposit $1,000 a day and $1,000 every 6 months for 12 years. 25 deposits, the final deposits made at the end of year 12. The savings account pays 7.4, compounded semi-annually. How much will you have at the end of 12 years? Notice that there's 6 months between payments. And even though they all occur over 12 years, N is equal to 25 payments. The interest rate is compounded semi-annually, and so it automatically fits the time between payments. Remember what we learned last time. If an interest rate is not compounded annually, it's not an annual rate. This rate is compounded semi-annually, so what we have is a 6-month rate equal to our stated annual rate divided by 2. 0.037 is the rate we use, in our annuity equation. 1,000 is the payment amount. N is 25, the number of payments. Okay, quickly, number 6. We're going to receive 15 annual payments of $500. The first payment will be received 7 years from today. Annual interest is 6% compounded annually. What is the value today? Notice that there's 1 year between payments. We're dealing with an annual interest rate, so it fits the time between payments. N is 15. So if I use my present value of an annuity equation, I'll get an amount of $4,856.12. That will be a lump sum amount, but where is it in time? Time what? Time 7? There's where we want to be real careful. The first payment's at time 7. 6, correct. We've consolidated the payments at time 6. And we need to move them from time 6 to time 0. And so let's take that 4,856.12 and let's move it backwards in time 6 years and put it at time 0 where we want it. At that point, it will have shrunk to $3,423. Questions? Again, it goes back to knowing exactly what the equations do. The present value consolidates the payments 1 period before the first payment's received. Now, this is essentially the same question, but for some reason, students find it to be much harder. You will receive 15 semi-annual payments of $500. The first payment's received, again, at year 7. So the interest now is 6%, but it's compounded semi-annually. What is the value today? 6 months between payments. The interest rate is 0.06 divided by 2, or 0.03, and it fits the time between payments. The present value equation $15 is the number of payments. When we consolidate that lump sum, it's $5,968. That's the equivalent lump sum for this annuity. But where is it sitting in time?
Sitting at your 6.
Okay. Not year 6.
Year 6 and 6 months? Year 6 and 6 months?
Yes. Yeah, but it's sitting one period before year 7. Well, the period is the time between payments. So the time between payments is 6 months, and this is at time 6.5 years. Right there, 6 months before the first payment. So I want to take this lump sum of $5,968 and I want to move it backwards 6.5 years. So I'm going to use my building block equation. The present value at time 0 and my interest rate is 3%. Now that's a rate that spans a 6-month period. So what is my exponent? Yes, 13. Because if this is a 6-month rate, how many 6-month periods do I want to bring this back in time? And I want to bring it back from 6.5 years, which is 13 6-month periods. Okay? Again, it's just following the rules, but for some reason, a question like that is very hard for students. But by the time this seminar is over, it won't be. Okay. Number 8 says you've been offered a contract that guarantees you'll receive semi-annual deposits of $8,000 for 10 years. First payment received today, and you'll get a payment every 6 months for 10 years. That means a total of 21 payments of $8,000. If you can guarantee an annual return of 9% interest compounded semi-annually, how much is this contract worth to you today? The interest rate is 0.045. It fits the 6-month period between payments. What we want to do is find what this stream of payments is worth today. There's 21 payments. Well, the present value equation I use 21 for my exponent. I throw the present value equation at this and we get $107,237.78. But is this the answer to the question? Is this tell me what the stream of payments is worth right here at time 0 or some other point in time? Where is the 107,000 sitting in time? At year what?
-1.
Yeah. Oh, well, actually, since there's Since there's half a year. Since there's 6 months between payments, it'll be a 6 month period before the first payment. So this is at time minus 6 months. And we have to take it, and to get it to time 0, we bring it forward. Oh, sorry. Now we just use our building block equation to do that. Semi-annual interest rate, one semi-annual period, brings us to time 0. And it makes a pretty big difference in this problem, about $5,000. And we were looking for an answer at time 0, so that's $112,063 is the answer. This is a very similar question. This time, you're going to receive your 21 $8,000 deposits. This is exactly like the question before it, but the first payment comes in at the end of the 5th year. So this is also similar to one we've done before. The interest rate, again, is 0.09 divided by 2. And again, we get that $107,237 amount. What point in time is that, though? We're trying to get everything to time 0, but where have I consolidated these payments? Come on. The first payment comes 5 years from now. There's 6 months between payments. So the present value equation has given me a lump sum amount at time 4 1/2 years. And I want to move it back. I don't want it to be at 4 1/2 years. I want it to be at time 0. So the building block equation, if this is a 6-month rate, how many 6-month periods do I have to have in my exponent? How many 6-month periods are there in 4 1/2 years? 9. So here we go. Okay. Any questions? The next few questions are about perpetuities. We'll speed through them pretty fast because I think every question is going to be just slightly different from the one before it. And the first one's very straightforward. What's the value today of a perpetuity of annual $300 payments The first payment is to be received 1 year from now. Interest rate is 6% compounded annually. Everything's perfectly set up for us. The interest rate fits the time between payments. The present value of the perpetuity is equal to the payment amount divided by the interest rate. So that perpetuity is worth $5,000. Okay. Now we have really the same question, but we're going to receive the first payment today. So if I throw my perpetuity equation at this, that $5,000 amount is going to be at what point in time? Minus 1 year. One full period. The period is defined by the time between payments, 1 period before the first payment. So that's at minus 1 year. And moving it forward, one period, we'll add $300 to the value. Okay? Another way to look at this would be simply, why don't I put my thumb over the first problem, or the first payment, and solve it? Now, all of these future payments, with the first payment coming a year away, they're all worth $500. I'll take my thumb off of this first payment that's right here at time 0, add it to the $5,000, and get $5,300 again. That might be a way you want to look at a question like this. I think of I don't want to confuse you, but any questions? No, we'll move on. Here are perpetuity of $300 payments. Doesn't begin until year 12. And so my present value equation is going to give me consolidate these at a lump sum amount of $500. And it's going to be at year 11. One full 1 year period before the first payment. So the building block equation we'll move that back in time 11 periods to put it where we want it. And the answer is 2,633.94. Okay. Any questions about perpetuities? You know, it's just a they're simple. The equation's a little simpler actually than an annuity, but all of the same rules apply. The interest rate has to fit the time between payments. The present value consolidates one full period before the first payment. And N doesn't appear in the equation. Well, let's go back to do a few annuities. In this one, Well, we're going to be editing that. What happened? I'm sorry. How long has it been like that?
Just did it.
I just did it? I don't know how I did it.
Did you change the input on the Alma?
I don't know. I don't think I touched the Elmo. I'm trying to get touch input 2 here. Signal, signal. Who knows how to work this thing? That's why I like chalk.
Then if you have to, just go ahead and use the blackboard.
Something. Okay, let me. Oh, that's working. I don't understand. I must have done something to the Elmo, but I don't know what I could have touched.
There it is.
Oh, okay. All right. Okay, we're back. Sorry about that. All right. This time we're going to receive 12 semi-annual payments of $60. The first payment will be received in 6 months. At the end of 6 years, the same time as the last $60 payment is made, we will also receive $1,000. If annual interest is 7.8% compounded semi-annually, what is this cash flow stream worth today? So, a little more complex problem. There's 2 parts. First, we have to take the annuity back to time 0, and then we're going to take the lump sum of $1,000 back to time 0. The interest rate .078 divided by 2, or .039. Now, since our annual interest is compounded semi-annually, it fits the time between payments. And since the first payment is 1 full period away, my present value equation is going to consolidate the payments at time 0 where I want them. There were 12 payments. And I get 566.38. Now the $1,000 is at time 12. So let's bring it back to time 0. Using the building block equation. If this is a 6-month rate, I've got to bring it backwards by 12 6-month periods, so that exponent here has to be consistent with the interest rate. And I get $631.85. And this is also at time zero. Because I have now found two amounts, the present value of the annuity, the present value of that lump sum, and they're both sitting at time zero, I can add them together to get an answer of $1,198.24. Okay. And just as an aside, what we've just done is we've solved for the value of a bond. And this is the timeline of a bond. And if you haven't had your first corporate class yet, you'll probably see that later. And that's all there is to it. Now we've got another problem that is somewhat complex because it's got two annuities. First, we're going to make 15 equal annual end-of-year deposits of $1,000 into our account. The account pays 10% annual interest, compounded annually. We'll make the first deposit in 1 year, so that our last deposit will be at the end of year 15. Then we're going to start making equal annual end-of-year withdrawals of $1,500 for the next 15 years. There'll be 15 withdrawals. The first begins at the end of year 16. What do we have in the account at the end of the 30th year, which is the time that last $1,500 is withdrawn? Notice we have 15 payments of $1,000 going into the account, 15 payments of $1,500 coming out. How much will we have left at time 30 years? So the strategy here, well, first, we noticed that there's 1 year between payments for both annuities. We noticed that our interest rate fits the time between payments. Now our strategy to solve this, I think, is probably pretty straightforward. Let's take everything to time 30. If I use the future value annuity for the first 15 $1,000 payments, I'll get a lump sum amount at time 15 right here. That's where this 31,000 is. Well, now I'm going to move that to time 30. By using my building block equation, and to grow this for another 15 years. So I have an amount of $132,000 at time 30. And actually, that's how much we would have in this account if we made those payments for 15 years, but never took anything out and just let that money grow. Okay? But I began to take out $1,500. So let's see what the future value of the $1,500 annuity is. And there's 15 payments there. That will grow to an amount of $47,658. Yeah. Okay. I'm sorry. The future value of the $1,500 payments or withdrawals is $47,658. Notice they're both at the same point in time. So I can take one from the other, and the result is $85,062.81. Okay. A little more complex. Do you see how that happened? Does that bother anyone? Because some students it does. But we can actually do this kind of leapfrogging through time. You know, I moved this amount from here to here as if nothing was going on in the meantime, even though withdrawals were coming out. But when I took these withdrawals and made them into their equivalent lump sum future value, it worked out. Though, again, the leapfrogging, I think you'll get used to it. These are just time travel equations. But I have had students, I've seen students, even graduate students, work a problem like this where they would go to take the money to year 15, then they'd move it to year 16, subtract 1,500, take what's left, move it forward 1 year, subtract 1,500 again, and keep going. And then the end of the test, they write not enough time. But you'll begin to get comfortable with this. Okay. This is exactly the same question, except we don't know. We want to know how big can we make these payments and we want to make them big enough so that we could end with a future value of 0 right here at time 30. The question is, how large can those withdrawals be? Exactly the same problem. And one way to solve it is, again, take all the deposits to year 30. That gets us our 31,000, but let's just go ahead and move it to 15 more years into the future. And we have our 132,000 amount again. If I make this amount the future value, of this 15 payment annuity of unknown payments, oh, okay. And then I can solve for the payment. If we punch this factor out in our calculator, we see it's 31.7725. Divide 31 into 132, we see that our payment can be $4,177.25. If we take this equal payment out, at the time we take the last payment, we will have exhausted our account. We'll have a balance of 0. Now, this type of a problem, where the money going into our savings account or whatever is equal to the money coming out, if it's 0 here at time 30, we can consolidate at any other point in this timeline. The money going in has to be equivalent to the money coming out. So I could have picked a consolidation point. Oh, time 15 would have been good. What if I'd made that future value of these 15 payments equal to the present value of the unknown annuity? That would have worked. I could have moved everything to time 0 and made the money going in equal to the money coming out. Or we could have gone out to year 100 and we'd have still been able to solve this. Often there are numerous ways to solve these problems. You don't have to employ every time the strategy I've used, and you may want to look for other strategies. If you don't break the rules, and if your strategy is correct, you'll get to the right answer, even if you don't do it the same way that I do it. Well, I promised you earlier I'd get you out of here before 5. This is probably our longest session. We'll save one of those problems for warm-up next time. I will see you Thursday. And we'll do a lot more hands-on work Thursday.